Welcome to Tech Surge News, where we bring you the latest in the world of science and technology. In this video, join us as we explore futuristic and groundbreaking tech that'll definitely knock your socks off. Nuclear fusion has far-reaching possibilities. It has the potential to provide power to the stars. If it can be recreated on Earth, it can provide nearly limitless energy with zero carbon emissions. In addition, unlike current nuclear advanced technologies, nuclear fusion produces no radioactive waste in the long run. For decades, it appeared that technology was just out of reach. Nonetheless, the payoff is so great that billions of dollars continue to pour into the field. However, Germany's leading plasma research facility has made history with its new nuclear fusion reactor, demonstrating that we are getting closer to the goal of nuclear fusion. The wonderful goal of fusion power, an almost infinite source of clean, renewable energy. What exactly is this new nuclear fusion reactor, and how does it work? How does this reactor compare to the groundbreaking ITER reactor? Physicists have taken another step forward in their attempt to create a nuclear fusion reactor capable of producing abundant, sustainable energy, or mimicking the sun. Fusion has been regarded as a kind of holy grail. If utilized effectively, it has the potential to be a source of clean and safe nuclear energy. Nuclear fission reactors separate atoms, whereas fusion reactors connect them. As a result, no hazardous radioactive waste is generated. In Germany, at Max Planck Institute for Plasma Physics, scientists activated an experimental reactor, generating hydrogen plasma in a device. The Wendelstein 7X Stellarator is the name of this device. The Stellarator is designed to hold plasma, which is created by slamming hydrogen atoms together and blasting them with microwaves until the matter reaches 100 million degrees. At this point, the atom nuclei fuse to produce helium. The entire process creates energy and reflects what happens at the core of the sun. The Stellarator's donut-shaped core resembles a miniature star. The device made its debut at the Max Planck Institute for Plasma Physics in the late 2015, exhibiting that it could keep a cycle of helium ions heated to 1,000,000 degrees for a tenth of a second. The helium ions running through the plasma reached a searing temperature of 40 million degrees Kelvin, 4 times hotter than in the subsequent experiments, which used 18 times more energy to power the W7X. In comparison, the sun's surface only heats up to 5,505 degrees Celsius. Do you have a sense of how potent the Stellarator is yet? While most of us are familiar with basic nuclear energy, which is produced by the breakdown of large atoms, fusion energy is produced by the fusion of atoms. It is the most highly promising energy source because it does not cause the same radiation problems as an atom trying to split power. Aside from the radioactive panels that line the interior walls of the reactor, fusion is the cleanest form of energy generation. We must deliver a powerful kick with 100 million degrees of rotation, which necessitates the use of a specialized machine. W7X is one of the 2 types of these that are currently promising. The electromagnetic fields produced by the resulting plasma are used by machines such as MIT's Alcator CMOD tokamak to keep the wriggling jelly donut of charged particles in place. Fuel injection creates enormous amounts of energy with a hot, slam-dancing cloud of particles. However, it is troubled by instabilities, making power generation a momentary affair. Meanwhile, stellarators like the W7X contain the plasma with banks of magnetic coils, giving them more power and enabling the hot ring of helium jelly to swirl for longer periods of time. Even though they don't quite match the Tomahawk's output, W7X's 15-meter wide machine appears to have demonstrated a way to bridge that gap. Another technology that is anticipated to usher in an era of nuclear fusion power is the ITER nuclear reactor. ITER is the world's largest and first machine of its kind, and it is currently under construction at Cadarache, a French scientific research facility specializing in nuclear power research. The machine would generate 500 megawatts of power by fusing two types of hydrogen, deuterium and tritium. That is 10 times the amount of energy required to run. ITER will have a diameter of 100 feet and a height of 100 feet when completed, making it a new type of nuclear fusion device. When the reactor and first plasma are completed in late 2025, it will be the world's largest magnetic containment plasma physics experiment, as well as the largest exploratory tokamak nuclear fusion reactor. Let's take a short break real quick. If you're enjoying the video so far, then why don't you give us a comment down below, because we at TechSurge News would love to hear what you think. Also, it would be greatly appreciated if you subscribe to TechSurge News while you're down there. On to the video. The Wendelstein 7X is composed of 50 superconducting magnet coils measuring approximately 3.5 meters in height. Instead of the tokamak's donut shape, the stellarator confines the plasma in a spiraling and twisting configuration. In the tokamak, electrons and ions are stimulated to flow around the tube as an electric current. A transformer-like arrangement is used to convert electric current. This current creates a vertical looping magnetic field, which, when merged with a field that already runs the length of the tube, creates the spiraling field lines needed. However, the tokamak retains plasma better than the other. To some extent, this is due to the symmetry of a tokamak, which enables particles to travel along smoother paths. Due to the large number of ripples and wiggles that stellarators encounter, it is not uncommon for large numbers of microscopic particles to be lost. Since the 1970s, this has resulted in the vast majority of fusion studies, ultimately resulting in the massive ITER reactor project. Higher temperatures are now possible thanks to the addition of graphite tiles to the internal wall of the Wendelstein 7X. This inside liner, known as a diverter, helps protect the twisting chamber walls while also allowing operators to pump more plasma in at higher temperatures, giving them more control over the density and purity of hydrogen plasma. The Wendelstein 7X stellarator has been maximized to demonstrate that power plants based on stellarator-type fusion reactors are feasible. To address the shortcomings of previous stellarators, a significant amount of theoretical and computational effort went into developing the magnetic field that keeps the heated plasma enclosed and away from the vessel's sides. One of the primary goals was to limit the energy losses in the plasma caused by the ripple in the magnetic field. Plasma particles, despite being bound to magnetic field lines, drift outwards and are lost in the process. Because of their symmetrical structure, tokamaks suffer only minor losses due to magnetic field ripple, small vortex motions in the plasma, as well as instabilities, which is also included as a loss channel, and stellarators all have an impact on the energy losses here. As a result, reducing neoclassical losses is critical for stellarator maximization in order to match the tokamak's good confinement properties. As a result, the magnetic field of the Wendelstein 7X was designed to reduce those losses. Wendelstein 7X has already been able to produce high-temperature plasmas and set the stellarator world record for high-temperature fusion products using the heating equipment currently available. This mixture of plasma density, temperature, and energy confinement duration demonstrates how close to the values for a burning plasma you can get. The detailed study of such a record plasma has now been completed. Despite the fact that turbulent losses were marginal at these high plasma temperatures, neoclassical losses attributed for 30% of the heating power, making them an important contributor to the energy balance. The effect of Wendelstein 7X neoclassical optimization has now been demonstrated in a thought experiment. The same plasma profiles and values that led to the record achievement Wendelstein 7X were expected to be achieved in plants with a less optimized magnetic field. The projected neoclassical losses were then computed, producing a clearer result. They would be greater than the heating power input, which is actually impossible. This means that the plasma profiles seen in Wendelstein 7X are only possible in magnetic fields with low neoclassical loss. The inverse is also true. Neoclassical losses were successfully reduced by adjusting the Wendelstein magnetic field. Tokamaks, on the other hand, have significant drawbacks. A transformer can only deliver a current across the plasma in short bursts, which is inadequate for a commercial fusion reactor. Current in the plasma can sometimes abruptly lose ground, resulting in disruptions, which are accelerated losses of plasma confinement that can unleash magnetic forces powerful enough to damage the reactor. Such problems plague even newer designs, such as a spherical tokamak. Stellarators, on the other hand, are exempt because no circulating plasma current exists. The fields produced by external coils are not required to be pulsed. Because of these two factors, some teams have stuck with the concept. Because the reactor does not generate heat by splitting atoms in a managed nuclear reaction, the power generated is virtually clean, despite the fact that the Wendelstein 7X cannot generate energy on its own. It will eventually be used to build a stellarator reactor that can run indeterminately, bringing us closer to a world powered by the same process that powers the sun. Thank you for staying around till the end of the video. To keep on hearing from us, feel free to subscribe down below and hit the bell button to get the latest notifications. TechSurge News, signing out.